And let's take attendance. Oh, must be in the wrong desktop. Let's fix that first. Boop, boop, boop. And then let's go down here. So please tell me that you're here, and let us begin. We'll see if I have to steal a mouse from one of these computers. Somebody took the one that I normally use. So the last things that we were talking about last time were testing. How can we be more confident that our programs are going to do the right thing, because programs doing the wrong thing has some consequences sometimes, right? So let's talk a bit more about that. I promise that there is a way to make correct software that cannot go wrong. Let's talk about that. There is a way to not have to try every possible input-output pair. There's a mathematical way to prove that your program is always going to be correct. So let's talk about how that works. All right. There are a bunch of different possibilities. So first possibility is you write redundant programs. I have heard that flight control software, for example, has a fail-safe, and there's 2 different machines that are trying to do the same thing, and they were programmed by different people, and so they're trying to agree on what to do, and that is called redundancy, right? They're checking each other. You can also write programs that check themselves. Hey, did this output lie in the correct range of what the output should be? If it didn't, maybe something's wrong. Okay, so that's programs that check their outputs. You can just add a little if statement. It's like a test in addition to the main program. That's something that you can do. Another option that you have is writing a proof. You can write a proof to say that my program is never going to do something bad no matter the input, which is nice to have. And that is very powerful. That is the topic of CSCI 26, if you get into that. So look forward to learning how to write proofs that your programs are always correct. Other options, you could, let's see here. When do we want to draw something? Okay, maybe this next one. You could also analyze a program. And these kind of go hand in hand, proofs and analyzers. You can write a proof that your analysis is correct. The idea of program analysis is that you kind of run your program using math and then prove some properties about it automatically, seeing if there are any issues. So let me try and explain what that means. So here's an example program analysis. Let me write some Python code. So x equals 42, and then x equals x plus 1. Do you see how you might be able to reason mathematically about this program? You could be you can write some kind of logic where you can prove what is true about the program after a given line has been executed. So for example, you know pretty darn well, right, that x is 43 here. And it's not a big jump to write a proof that that is the case. Okay, that's all. So that's something that you might like to have. Okay, that's a program analysis. That's one way to prove that software is always going to be correct, that the output's always going to be what you expect. You could also specify what your program needs to do. And there are specification languages in addition to programming languages. So one language is, it's European, so it's called Z and not Z. What you do is you say what you want, and then you program it. So let me try and explain that too. So here is an example of a specification language. You encode that there is a requirement on your program. The output should always be, you write this in your little specification language, the output should always be greater than or equal to 42, something like that. And and then you go off and write your program, and it will match the specification. That's one way to have some more guarantees about what your program is doing. But I think you kind of get the idea. There's some other way of saying that your program is correct. You either write a proof outside of your program, you run an analysis, that's a program that's trying to run your program. You write a specification, that's a mathematical formula for what your program is supposed to do. Those are all the different ways. There's plenty more to write correct software. And I think we've noticed that they all require you to do something new, to do extra work, to specify what you want, right? You have to specify exactly what your program should do, what it can do, all that stuff. And sadly, that leaves room for more bugs. Oh man, because you could maybe write an incorrect specification, couldn't you? You could say, oh, the requirement should always be that the output is always greater than or equal to 45, when really it should have been 42, and things go wrong. So if you miswrite your specification and you prove your program correct with respect to it, it still means nothing because you got the specification wrong. And so you have to somehow verify that too. So it's turtles all the way down, and it's a hard problem to solve. Are there any questions about it? Writing correct software. I think the real answer would come in CSCI 26, if you're willing to wait for that. All right, so that's a lot of words. Let me give you some more examples before we have a little debate, because we've talked about a bunch of weird stuff. Let's debate about it soon. So let's talk about air traffic control. This is an example from your book. So there is this cool thing, this cool piece of software. It's called the Traffic Collision Avoidance System, which I assume is pronounced TCAS when they abbreviate it like that. It can figure out if you have two planes that are trying to fly close to each other. It can figure out if they're at the same altitude, they're about to hit each other eventually, they're going to run into each other's path, and that's a bad thing, right? And so it predicts that and tells pilots, hey, you should do this thing to avoid crashing with this other plane, right? So it's in every airplane. They are connected to this TCAS system. So let me draw my best airplanes. So here's one. It's flying. And here's another plane that is about to hit it, for example. This system would do something like this. It would say, hey, plane 1, you need to decrease altitude. Hey, plane 2, you need to increase altitude, and then they'll miss each other, right? So that's what this system would do to help the planes avoid crashing into each other, and everybody has a nice day. Sadly, this is software, right? It wasn't perfect from the beginning. The original version said too often, a lot of the time, that, oh, these planes that aren't really ever going to crash, it warned them, hey, you're probably going to crash, you should avoid. And that was an issue because it was kind of crying wolf. Right? So these pilots who were looking at this system trying to not die, they saw that it was wrong so often that they stopped trusting it. Okay? That is very unfortunate because it is a nice thing to have. I think we can all agree. Eventually, they improved the way that it worked, and it was able to perfectly accurately say, okay, these planes really are going to crash. Let's move them in this way, and everything will be okay. And sadly, that was after all of this false alarm business, which meant that people stopped really looking at it. So a collision happened when one pilot followed the system, said, okay, I'm going to trust the system. I believe it. It's going to tell me what to do. And the other ignored it and instead followed what an air traffic controller said, another human who you would expect to be more trustworthy, right? Unfortunately, that resulted in them both doing the same thing, going back to the same level and path, and that caused them to crash. So that's very unfortunate. So nowadays, in fact, everyone is required to disobey the human and obey the system that's trying to tell you if you're going to crash into another aircraft. So that's kind of like a win for software, I would say. It got so good that you were required to follow its suggestions. But it took a crash to get there, which is very unfortunate. Any questions, comments about that? This whole set of slides is kind of sad, which is unfortunate. There's no real getting around that. So I've shown you a bunch of examples now, and I think it's time for a little mini debate amongst ourselves. So please go to the written ice page. Let me clear it out with my trackpad instead of my mouse. I will do my best. But I want you to think about this kind of stuff. all these issues that we've been talking about. I'm sure there's more that we haven't talked about that you have maybe heard of. There's a lot going on. I want to hear what you think. So my question to you is, do we depend on computers too much? Should we maybe depend on them less, like for voting, for air traffic control, for crash testing? Maybe they're a little bit too much in our lives and we would do better without them. So please try and write as a group one argument for this idea, like yes, we do depend too much on computers. Tell me why you might think that. What's one good argument why? And then one argument against it, like no, computers are actually helping us, and this is my reason. Okay, so give that a try. Think both ways on both sides of that question, and then we'll come back and discuss. So please take a few minutes to do that. Take about one more minute. It was extra loud for some reason. All right, I hope that was enough time. Let's take a look. Does any group feel very strongly about what they wrote and would like to share? Or shall I pick randomly? Yeah, do we depend on computers too much? Why or why not? I always like to go through the middle group, so let's look at the end groups. Let's word wrap this. Wrap. All right. Forward tech advancing. Cars have been a big example of trusting computer software too much. Oh yeah, so we have like self-driving cars. That's a scary subject, right? It's not been researched enough for us to rely on vehicles to carry programs such as autopilot. Yeah, so that Tesla stuff. That's out there, and people are getting a little cocky and not actually keeping their hands on the wheel like they're supposed to, right? Even though it's not yet certified. So there's a lot there. That's a good argument against. So, or a good argument for us depending on computers too much. Maybe we should tone it down a bit. Wait until we can verify things better. Let's take a look at, let's do group 6. Computers are much more dependable than us. Yeah, that's a good point. Computers, they don't get tired, right? Unless there's like some kind of electrical surge. So they can last longer, they can do fancier things, they don't mess up as much as us, relatively speaking. And on the flip side, computers are ingrained in our current society. And if something were to happen that knocked out our electricity, have you guys heard of that like horror story? If there's like a solar flare that's super powerful, it's going to knock out the whole power grid. Apparently that's a thing. How would we live? Who knows? If something were to happen that knocked out our electricity, we would regress back to before widespread computer usage, making everyday life much harder as a result. Yeah, so that would be difficult to get back on our feet in the event that something horrible happened to our computers. So maybe we need fail-safes. Maybe we need something, even if we're using computers a lot right now, maybe we should have something in place so that just in case something went wrong, we are ready. All right. These are good ideas. 4, computers are becoming a crutch. That's true. It's easy to do your math homework these days on Google. Are we really learning? Things like that. Any event that lessened the availability of computers. Yep, that's a great point again. So if something happened to these computers that we're relying on, that's a huge issue, right? And then on the flip side, that's a great, these are good common points that we're all agreeing on. Computers are very infallible, generally. So if you program something right, the computer will follow that program to a T and actually do everything as expected. It won't miscalculate things. Assuming the program is correct, though, and maybe that's a big assumption. Yeah, these are great points. Any questions or comments about this before I move on? All right, glad to get us thinking. That's the whole point. So let me try and talk about how I might approach this question if I had like an essay on it or something. So maybe it really could go both ways, right? So maybe we don't depend on computers enough, especially with that air traffic example. It's really helping us there, saving lives. But you can always ask the question, hey, should we be using computers at all? So if we ask our famous philosophers, we can see what they might have thought, and that can help us approach the problem. So if we ask Kant something like, should we always look to computers to solve our problems? He probably would say no. Like, you can do what you want, dude. You have free will. So if you don't want to use a computer, no one's going to force you to. But I think you could also ask a similar question to Kant with the word always in it. That would get him to say yes. There's definitely ways to frame this problem in a Kantian way. And then Mill, again, is all about utility. So how are we going to weigh the utility value of using computers and keeping them in our lives versus ripping them away, right? So I think Mill would say, yes, these things are improving our lives. They're making a bunch of different new jobs possible, things like that are helping humans, right? Helping them much more than it's hurting them. So I think Mill would be a resounding supporter for computers and using them in our everyday lives. So that's what I think there. I think one of the main issues came back to safety. I talked about a bunch of examples where computers kind of messed up in the safety realm. There are plenty of examples, though, of computers really keeping us safe, okay? In cars, for example. Think of how, horrible it would be if we didn't have ABS in most of our cars. It's standard these days. I think it's required by law, right? My first car didn't have it, so I was afraid I had to pump that brake if I ever had to slam on them. So that's going to keep us safer. The check engine light, cars didn't used to have that, right? If the engine was going to blow up, it was just going to happen one day, and you didn't get a little nice light to tell you that. So that's really helpful. Computers really are making us safer for some definition of safe. And then airplanes, of course. We have TCAS, keeping planes from crashing into each other. We have autopilot, so that tired pilots don't have to man the little plane steering wheel all the time, whatever that's called. That helps keep them or everybody in the air safe, right? That's very important. Home security systems, that's a thing that a lot of people care about these days. And that, I guess you just had to buy a bunch of dogs, right, before home security systems were a thing. I think that is a bit cheaper to use the electronic version. What else? Phone passcodes. Even though somebody can maybe force you to unlock your phone, there is a passcode that's blocking it from most people, right? And then finally, most of our financial lives are on the internet. I heard somebody talking about Bitcoin, things like that. But even banks, right? I get paid electronically. I'm sure most of you do too. I don't go into the bank to deposit a check. I just do it on the app, right? So how do they know that we are actually ourselves, that these owners of these accounts? Well, you have to have a password. Maybe it sends you a text with two-factor authentication or something. But that's keeping our financial lives safer, because maybe back in the day it used to be a lot easier to impersonate somebody, go into the bank, say, I want all of my money, and you weren't actually you. So I think computers are helping us in that way too. Any last questions about these ideas before I switch to some new slides that talk about slightly different things? All right, enough bad stuff, okay? Let's talk about something kind of more upbeat. So let's talk about artificial intelligence. That's a cool buzzword that I'm sure we've heard about. So let's get into that a little bit. And I don't think we have time today to get through the whole thing, but I'll at least show you a few cool things. So let's first talk about Moore's Law, which you may or may not have heard of. It has to do with how fast computers are getting faster, okay? And I promise that question makes sense if you stare at this question long enough. How fast are computers getting faster? The answer used to be pretty fast. So here's the idea. Moore's Law, it was I guess it's something that somebody noticed, something that tended to happen. This was observed by a man named Gordon Moore, who was one of the co-founders of Intel. And he noticed that the number of transistors in a chip doubles every about 2 years. And if you understand what that means, that's an exponential function, right? So if you start out with one CPU year, or one transistor year 0, then 2 years later, now you have 2 transistors. 2 years later, now you have 4 transistors. 2 years later, now you have 8 transistors, and that's an exponential function that keeps growing very, very quickly. Okay, so that's what he noticed. And we talked a bit about transistors. They're not exactly processing power. They're not exactly equivalent to the processing power of a CPU, but they're close enough. For a while, this idea of putting more transistors onto a chip meant that computers could do more things. Okay? You can use transistors to build the logic gates that we talked about in class, those little circuits. So you could have more of those, which means you could do more work, essentially. So yeah, double the transistors, double the speed for the most part. That happened a lot. And eventually, though, that speed stopped getting fast. Okay? We started running into weird little physical issues like quantum issues. We started running into power limits as well for processors. So I think we've maxed out around like 4 gigahertz for a normal processor. Any more than that is going to require ridiculous amounts of power and heat dissipation that we just don't want to manufacture for consumers. Okay, so that's kind of how fast CPUs have become, and they've kind of bottomed out at that speed. But we got to keep going faster, right? So what did people do? They started putting a bunch of cores inside of a CPU. Have you heard that term before? It's just like mini CPUs, little brains inside a big brain kind of thing. So that's when multi-core started to happen in like I want to say the early 2010s or something like that, around then. So here's like one big CPU, and here's what multi-core means. You put a bunch of little chips, a bunch of little baby CPUs on the big one, and they all work together. All right, so these days, like maybe in this laptop, there's like 4 2.5 gigahertz CPUs all working together, all thinking different things. Okay, so that is where we are now, and it's still, you add more tiny CPUs, you add more cores, you add more power, add more processing power. It's just the speed of those individual tiny processors is not getting much faster right now. Okay, but you can always add more. You can scale up, things like that. And you have to wait until CSCI 45. Sorry to be throwing different CSCI classes on you right now, but we get into this a lot more in CSCI 45 if you get there. Okay. Another issue is the way that you get more transistors on a chip is you make them smaller. They have become so small now that we're running into quantum issues with just like stray electrons. They're that tiny. They're microscopic. They're just a few molecules wide. So we're eventually going to hit an atomic wall, which means that we cannot make transistors any smaller. But it's been a very fun ride. We've had very fast computers come out of this deal. Okay, so let me show you this little graph. And first, I want you to notice that, let me explain the axes. And I want you to notice something about the axes, because this looks like a line, right? So here's time, conveniently displayed in 2-year increments. And here is the number of transistors on chips. This is what the other axis is. And notice that this axis is increasing exponentially. It's a logarithmic scale. Okay, so a straight line on this graph means an exponential graph, really. Okay, so we want this to look like a straight line, and it will prove Moore's law is true. And so let's go back in the day and talk about numbers of transistors. These are like the granddaddies of like our Intel CPUs, the 8008, the 8080, all that stuff. Very popular back in the day. Only a few thousand transistors. Crazy. Motorola 6800, that was like in one of the first Apple computers, if I remember correctly. But notice that just a decade later, 1970 to 1980, now we had almost 100,000 transistors on a chip. Much, much faster. It used to be the case where you could just wait a couple years, buy a new computer, and every program that you had previously bought was like a million times faster. That is no longer the case these days, sadly. Yeah, here are like the first ARM processors, the ones that are in our phones nowadays. They started out, and they didn't have a lot of transistors. And then Intel started packing more. We had million transistor chips starting in late 80s, early 90s, all this stuff. And we kept on moving in a straight line. I think you can see that this is a straight line, right? Which means it's an exponential curve. And we're up here now. Whee! And look at when we started adding cores. It's these ones around here. That was what kept it going, kept this rule going and allowing us to have more transistors, just bigger chips and faster speeds. And so here is where we are up here now. We've got a bunch of cores on a computer, but they're not going much faster. But look at this nice little line. That is a total exponential curve, and it's been a fun ride. Any questions about this? Transistors on a chip, things are getting faster, but you can see that we've started to we're starting to bottom out. Which is nice for us. We buy a computer and it lasts a lot longer these days. Did not used to be the case. All right, are we ready for some artificial intelligence? Let's see how far we're going. I also want to talk one more thing about your essay that I assigned last week. Just give you a little hint on it. So let's talk about artificial intelligence now. So that is all about asking a computer to pretend to have a brain and ask it to think for us. How in the world does that take place? How can computers think? I'll try and answer that. And then we'll talk about how good are they at it. Maybe you've heard some examples. We'll talk about those too. So first of all, let's figure out what in the world is artificial intelligence, or AI for short. Well, it really is just when machines think. So you give them some sort of way of noticing something. They are able to perceive their environment. Maybe they have a camera or a sensor or a microphone, whatever senses you give them. They take that, perceive their environment based on those sensors, and they make choices, right? Perceive environment, make choices to achieve their goals. So you program your artificial intelligence program with some goal in mind, like, hey, I want this weird-looking robot to be able to run or run this far over here, carrying this amount of weight, stuff like that. So this is a very utilitarian concept. They want to do good, right? Every artificial intelligence program wants to achieve its goals and do the best that it can for its definition of good. Okay? So there are a ton of different versions of AI, of artificial intelligence, and there's definitely not enough time to talk about all of them, but there's plenty of little subfields, and I'm sure you've heard about all of them, at least a little bit. Like robotics, first of all, you try to make a mechanical human, right? You've seen all of those little Android devices and robots. This one's made by that weird company called Boston Dynamics that makes animal-looking things that walk and prance around, and they have cool music videos. So that's a thing. There's also machine learning, which I'm sure all of us have heard that term before, right? And what that does is it's capable of things like face recognition. The USPS uses it to recognize writing on letters to see where it needs to go, where what you're sending needs to go. All that is done by machine learning. And then a subfield of machine learning that we'll talk about is called neural networks, is when we write a program that models what a human brain does with its little neurons talking to other neurons. We'll get into that. And then you could also just say that artificial intelligence is glorified statistics. If you ever read an artificial intelligence book, it's going to teach you a lot of statistics, because really the idea of making a choice inside of a computer is to weigh your options and to predict the best one to do. And so that's a statistical test a lot of the time. Even though it doesn't sound very cool, we like our neural networks better, but a lot of problems can be solved just by plain statistics, regressions and things. So yeah, that's artificial intelligence. Are there any questions about any of these terms, any of these ideas before I get into more of them at a finer grained level? Okay. Here we go. So yeah, I just have a few examples, and that'll be the rest of today. I think I do have a fun activity, though. That'll be nice. So here are some examples of artificial intelligence. Probably the first one that became available to just normal consumers was those early digital cameras with blink detection. Every camera these days draws a box around people's heads, and they also were trying to figure out, hey, did somebody blink in your picture? Oh man, you're going to have to take the picture all over again. So blink detection happens to be a machine learning technique. And I just noticed that I didn't zoom out all the way when I was looking at our graph. Okay, so blink detection, it's machine learning. It's asking a computer to figure out where a human is in a picture. The sensor is the image. Or it's reading the lens and creating an image. And okay, let's talk about that, because what needs to happen, right, is it needs to take the picture that's being seen from the camera lens. It needs to figure out what's in it and discern, okay, here's a person, and then somehow notice that, okay, the head's here. It draws a little imaginary box, which sometimes in real life on the screen becomes a real box. And then it needs to draw boxes around the eyes because it needs to stare at those to see if they're open or closed. And then it needs to figure out what in the world does it mean for eyes to be open or to be closed. And we'll get into that in just a second. So yeah, let's see. What do I want to say here? Okay, so yeah, you might be wondering, what does it mean to do machine learning now? Because that's a subfield of AI that's very popular. Let's talk about it. Let me try and teach you what machine learning is and how you do it at a CSCI 1 level. Okay, so here is the way to do machine learning in essence. Okay, you use a bunch of cool libraries in Python, for example. You're standing on the shoulders of giants, but this is essentially what you need to do. All right, if you have some goal, some task, you have some input, and some process that you want to perform. So let's pretend it's blink detection. Okay, so what you do is you make first a giant set of what's called training data, because you're going to train your artificial mind in your computer. You're going to have it learn what the difference is between these pieces of training data. And usually you will label that data with what you want. So you're going to take a bunch of pictures of people with their eyes open, right? I don't know. That's my best drawing of people with eyes open. So you're going to have a bunch of pictures like that, just in different backgrounds, different lighting levels. And then you're going to take a bunch of pictures of people with different backgrounds, different lighting levels, with their eyes closed. Okay? And of course, you're going to make group pictures as well, because it needs to notice everybody. That's essentially what training data is. You're giving it all the things that you want it to be able to classify, to determine the difference between. So usually you'll label the data okay, these are the good pictures. Those are the ones with the eyes open. These are the bad ones. These are the ones with the eyes closed. We don't like that. We want to alert the user if they ever take a picture with somebody with their eyes closed. And so yeah, if you want to notice faces, you want to give it a bunch of labeled pictures with faces and non-faces. You give it a dog, you give it a picture of a clock, you give it a picture of these slides. You want it to be able to discern whether or not the thing we care about, a human head, is in there. Okay? So that is the idea. So you'll give it a picture of a face, and you'll give it a picture of an airplane. And hopefully it won't think that the airplane's eyes are open or closed. It will just not even try. Right? So that's step one. Get a bunch of good training data. That's important. That's probably the most important step these days. The second step is to train your machine learning tool. Usually that's called a model. That's your little virtual brain that's thinking. We call it a model. And you use some machine learning technique to do that learning, to do that training. It's like it's working out, right? You're building that brain, making it strong. One way to do it is using a neural network, which we'll talk about later. That's a fancy way that's popular these days. And usually the idea is that your model is really bad at the very beginning. You give it a bunch of random ideas and it's not really sure what to say. Okay, it's going to predict that everybody's eye is open even if it's an airplane. But the beauty of machine learning, and it's hard to get into this in this class, is that it's able to learn from its mistakes. These machine learning techniques are able to learn from their mistakes, saying that, okay, on this training data, I got this one wrong. Let me try and figure out why. Let me try and make sure I don't get it wrong again the next time I train on this data. Okay? So usually the model sucks at the first time you try it, then you keep running it on itself on that same training data, and it starts getting better and better. It learns from its mistakes. Okay? I'd be happy to talk more offline about this, but it's a bit of a complicated process. But yeah, neural networks, for example, they're like little models of the brain, and here are neurons that are talking to each other, sending information. and the output maybe is like, oh yes, there was a face, something like that. So it's wiring the brain as it's learning. That's essentially the idea. It's wiring its little virtual brain. And then finally, once you trained it enough on your sample data, hopefully it got really good at noticing that, oh, the eyes were open in these pictures where they really were, and the eyes were closed in these pictures where they weren't. And it's like, there are no heads in the pictures of airplanes and things like that. So eventually you're going to get to a nice looking model on your training data. And then what you do is you test it. You actually go into real life, or maybe you have a bunch of different labeled data, emphasis on the different so that it's not memorizing the real answers. You test your model on a separate set of labeled data. That's the key, because you don't want it to just memorize answers for those particular pictures that were in the training data. And yeah, you just keep doing this process. You make sure that your model is eventually getting things right most of the time, and that means it's learned good enough. And you can package that idea, that virtual brain, inside of your tiny little consumer camera. Okay? And that's the idea. That's what it does. And I guess eventually it's going to learn how to figure out if eyes are open or closed. And the goal is to look for like an oval shape, because that's where the head is. That's essentially what the neural network will learn. And then it's going to find eyes within it. And those are at like 2/3 up. If you separate based on the nose and the chin and the eyebrows, things like that. That's where the eyes are. It will learn. And then how in the world does it figure out if they're open or closed? Well, I think you can tell that there's a big difference. And a computer can also learn that difference between an open eye and a closed eye, because you can see the white of the eye if there is an open eye. Yeah. And so it's looking for whiteness surrounded by skin color. If it just sees skin color, then it's going to think that the eyes are closed. That's essentially what it's learning. So that's machine learning in a nutshell. There's a lot to go and talk about, but that's my quick intro to it. Are there any questions about these ideas? Yeah.
So like when you're trying to sign in on the website, it's like, oh, prove you're not a robot. Mm-hmm. You're like essentially like doing training data for them. Like you're clicking the picture, like which one's a bus and which one's not a bus.
That's very true. Yes, that's one way. That kind of service, if I do remember correctly, it is for training and labeling machine learning problems.
So like they're getting, I guess, data from us that way, or is it like an actual verification thing as well? I remember hearing about the thing where they transcribed the entire like newspaper, where like before you had to newspaper of like letters and words, and they based on like first like two sets of words, or a set of two words. The first word being the one actually train and test you on, because like they know what that is, and then one that if they assume that you have.
That's right. Yeah, I've heard that.
If that's correct too, then they would actually pull that with a massive data with other people, and that's how they transcribe like thousands of words like every day.
That's super cool. And so like that's like a win-win situation for the people who are making that service for authentication. Like they're getting labeled data out of the deal. They know where the bicycles are in this picture, but not this one. And so if you get the first one right, they think you're a real human, and then they trust your opinion on the second one. And then the other, the company that's using that authentication service is actually making sure that humans are there. So that's, yeah, it's really nice, but it's a weird idea. That's a good thing to bring up. Any other comments, questions? This is fun to talk about. The internet is weird. Machine learning is weird. Computers thinking. So I want to teach you neural networks. So let's talk about virtual neurons. So please go to this website. It's called playground.tensorflow.org. Please type that in and go there. Hopefully it still exists. And then I'll show you what I want you to do with it. It's a fun little exercise. So neural networks, remember, I tried to explain that they are modeling neurons and their interconnections in a brain, in a virtual brain. And so this website allows us to play with that virtual brain and actually solve some real problems like what you might see in the wild. So it's playground.tensorflow.org. Hopefully everybody who wants to go there has gone there. Let me pull it up myself. And here's what it looks like. Let me make it normal looking. Dun, dun, dun. So this is a neural network, okay? Here's what it does, and here's how it looks. So here are your inputs on the left side. X1, X2, X12, X22. All these things are different inputs, and I guess the original inputs are X1 and X2, and then the rest are like combinations of them. In certain ways, they're multiplication, things like that. The sign of X1, the sign of X2, maybe that's helpful. So those are little pieces, because our idea is we're trying to classify things. We're trying to say, we're trying to find the difference between the blue dots and the orange dots. Okay, that's the machine learning goal for this simple website example. Okay, we're trying to figure out the difference between the orange dots and the blue dots, and our input is where the dot is. So you can think of x1 as the x coordinate and x2 as the y coordinate. Okay, and like x1, 2 is like their multiplication, or this one is the multiplication. One's the sign of x1, one's the sign of x2, stuff like that. And so that's your input, and you can choose which pieces you want as inputs to your neural network. Maybe you only need x1 and x2, who knows. And then you're allowed to add a bunch of interconnections. These are like neurons that are talking to other virtual neurons. And you can pick as many as you want, doesn't really matter. But the end goal, the idea is you want to be able to determine whether or not in the last stage, and it'll draw a pretty picture, maybe I'll do the first one with you, it'll draw a pretty picture around and separate the orange ones from the blue ones. Okay, that's the goal of this idea. And here are a bunch of different data sets that you can play around with. Here's a spiral, here's 2 dot clusters that are not very connected. Here are like a checkerboard pattern of dot clusters, but you want to be able to separate the blue from the orange. Okay, so let's go back to this one. And so that's the idea. You want to set up your neural network in a special way. Think of the features that you want, the inputs that you want. And the output is always going to be, I think, just 2. Pretty sure you can't do much more than that. Is it blue or is it red, essentially? But play around, add buttons, add hidden layers, and then you press play. And this causes it to learn. Because right now, I think you can imagine this is like its output. It's kind of faintly blue in some corners and faintly orange in some other corners. You can tell that it really sucks. Like its test loss means how good it was. How many times did it get it wrong? What's the percentage? So like almost 50% it got it wrong. That's in the first round of training. You can press play to run a bunch of rounds of training. And look at how it gets better every time, and it learns from itself. So it's wiring up these neurons, which are taking these pieces of input in a special way, and trying to classify whether or not the blue dots are blue and the orange dots are orange. And it looks like my very overkill brain got it right for this particular example. The goal, though, is to have as few little layers and as few output, or as few neurons as possible, okay? Because that's more efficient that way. But that's how you train, and that's how you do a real-life machine learning problem. Based on input, pick some features, pick some interconnections of your neurons, and press play to start learning. Okay? So play around with this. Try each data set. See if you can get the fewest number of little hidden layers. Maybe you only need these many. Oops. Usually need an output layer. What do you need to actually classify well? You can see that this choice, which was less information, doesn't do as well, even though it's training a million times on itself. So some virtual brains are better than others. But this is the coolest example that I can find that you can understand. So take a couple minutes, try it out, share your best ways of finding these answers, this classification problem, that's the technical term, with each other, and then I'll check back in with you. So go forth and play with the data and neural networks. And while you do it, I'll see if I can get the smallest thing to learn. That doesn't seem to be working. How about these two? Oh yeah. So beat that. and then also do it for the other data, of course. So you as a machine learning scientist, you get to pick what features, what data you want to use as input to your virtual brain, what do you want it to see, and then how do you want it to talk to itself? How do you want to interconnect and wire up your brain to make sure that it's going to do the right thing as fast as possible? Yeah, so take a couple more minutes to do that, and then I'll play around at the same time. Not that by itself. Cool. Alright, I hope that was fun. Did anybody get the spiral pattern with as few features and hidden layers as possible? It looks like it's impossible to do it with just a single layer. And the idea is, if you mouse over these, it's like how much influence these previous features / neurons are, like, how much weight is being given to their idea, to whatever they're trying to figure out. Like, this is the picture that it's looking for. This is the picture that it's looking for. How much does that help in the output? That's kind of what the idea is there. Is that enough? Oh. Yeah, I can't really. When in doubt, you just add a bunch of layers and a bunch of features, and eventually it will work. Maybe I need a million outputs as well. But one of the big issues with adding just pressing the plus a million times is the idea that it will eventually just memorize the answer. That's called overfitting. We don't like that. That's why you want as few things as possible to be used, because this is obviously not the right picture, even though it seems to be working well for the input. That's called overfitting. We don't like that. So yeah, there is a way, but that's neural networks in a nutshell. Are there any questions about this? Yeah.
So we're like making neural networks with like actual code and stuff. Is it like majority just Python?
There are a lot of good libraries in Python. A lot of people like to use Python because of the libraries, but there's plenty others.
So it's not like you have to do it.
No, it seems to be the standard thing, though. Like, people are flocking to Python because of the library support.
Okay.
And also because Python is like a good, easy first language to learn. And so a lot of people who are not computer scientists that want to do some kind of machine learning, they will go straight to Python because maybe that's what they learned in school.
What about the speed? Does it like matter really at all
For machine, it really depends. Machine learning can be sped up by like going and using a GPU instead of the CPU. And Python libraries are capable of doing really fast things. A lot of Python libraries aren't written in Python, if that makes sense. They're written in a lower level language like C or C++. And so at that point, you're just using a library function. It doesn't really matter. It's going to get the speed of whatever language it was really implemented in. Yeah. Any other questions? Kind of looks like the Python logo. All right, so this is an example of overfitting. We don't like that. But here's how the brain is wiring itself. It's learning things like a human might. Okay, so yeah, I just have a bunch of other examples, and that will close out the day if we're doing okay. So here's some examples of machine learning. So we've talked about how computers and programs are really good at like getting the right answer, of always doing the same thing. Factory robots are one great example of that, right? Because you could program a machine to do the same exact task over and over again, and it's never going to get tired or complain, right? That's the idea. It's never going to fail unless it fails catastrophically, most likely, right? Super tiny chance of failure, works much faster than a human could, more precisely than a human could. And I guess the only downside of using these cool-looking factory machines is that they cost a lot of money up front to build, to make them work and do their very specific task. So that's unfortunate. But I guess the whole idea of them is to replace humans, to be a better human. And so I guess they don't have to pay as many of them, so they can afford these fancy machines, which, again, is maybe a social issue as well, because people are losing jobs now to machines. That's a problem. But yeah, factory robots can do very fancy things very precisely, like move this lever from here exactly 5 degrees, no more, no less, on the dot to some very small amount of, or some very high amount of precision. That's what these things can do. Much better than a human could. Much quicker. Okay, so that's factory robots. Those are taken over. Probably the most like the coolest version of artificial intelligence is like a computer that can actually think and respond, right, and do things. Maybe you've heard of this Watson computer that played on Jeopardy, for example. That's a good example of maybe what you might think of an intelligent computer to be, like something that is really mimicking a human. Okay, so let's talk about Watson. Definitely feel free to watch these YouTube videos. I don't think I can play them for you because I'm recording right now. I'm going to put this on YouTube, so that might just ruin my account. So I'm not going to go there, but totally watch them yourself. And yeah, Watson was made by IBM back in 2005, and they started trying to make some general purpose artificial intelligence for this. So what Watson does is he uses natural language processing, a very cool term, to figure out what's being said. He's looking at the Jeopardy screen, he's reading the text there, and it's deciphering that text and figuring out what question is being asked. It's trying to figure out all of that. And so that's natural language processing. It's breaking things down. It's trying to figure out, okay, here's a subject, here's a verb. What does that mean based on what I know? Okay, so that's what Watson's doing. And once it figures out what the question is asking, it tried to answer it based on a huge database of information that is much bigger than a human could ever store in them. For example, when Watson went on Jeopardy to compete, and he eventually got really good and beat all the humans, right? It had all of Wikipedia in addition to many other sources. Okay? So that is not something a human can keep in their mind, right? So the idea of Watson is use this natural language processing, figure out what is being asked, and then statistically, because machine learning really is glorified statistics, it comes up with a bunch of potential answers. It's like answer 1. What is this? Answer 2. And this really is just trying to map English text, which seems difficult, to ideas, to answers. And so it's like, oh, maybe answer 1, 10% chance that is the right answer. Answer 3 possibility, maybe that's 5% chance that's the right answer. And then like answer 2, there's an 85% chance that based on what I know about this question and my database of knowledge, that this is the right answer. And then it just goes and picks the best one. So maybe if it has enough confidence, over like 70% for one of its answers, that's the one it says, and it usually gets it right. Okay? So it won against humans eventually, just because it was so fast. It could parse the English question, consult its database faster than a human could press a button. Any questions about that? Do we remember that? Maybe that was... I didn't watch it when it was happening, but I definitely watched all the YouTube videos about it. Did you see it?
Oh, yeah. I've watched it every
Oh, nice.
14 years. It was incredible, but I think Watson was the first 2 episodes.
Yes. Yes, Watson.
And that was cool to see how a lot of people assumed he would just be immediate and be able to get every answer that was loggable.
Mm-hmm.
It was really cool to see that there was actual work and knowledge that he sort of grew.
Yeah, so you need more training. You need more fine-tuning to be done with his little neural networks, for example. Yeah. Awesome. Anybody else have any questions or comments about this? Because there's Watson that comes to mind, just asking somebody about artificial intelligence. And then there's like chess and Go and all those board games that people care about computers beating humans at. So let's talk about that, and I think that'll be it. So in 97, back in 1997, it was crazy. I was not very old at the time, so I don't really remember it being so crazy, but it was a huge deal apparently. Back when a computer, for the very first time, it beat the world champion at chess. Okay? And that was something that had never happened before. A computer became smart enough to do the right thing. Okay? And that is crazy. There are a lot of different options in chess, right? Just to imagine the way that the game could possibly unfold. There's a bunch of different options. So here's the idea. Here's how a computer might play chess. It's like, here's the current state of the game board. And here are all the different moves that could be made by the current player who needs to go next. And so it has to think about what could happen from this game board. What could happen from this game board? I mean, that's what a human does too, right? What could happen from this game board? And then it goes even further. Okay, it's the next player's turn. Assuming this move got made, what happens here? What are the next valid moves? What are the next best moves? And so it draws something like this. It's called a tree because it looks like the roots of a tree. And you can imagine that it gets very deep as much as the computer's memory can store. It's trying to figure out what could happen as the game gets played in a bunch of different ways. And it can hold on to that, all those different options in its mind a lot better than a human can because it has more memory, at least at this level. And it was able to pick the right path. It was like, okay, if I make this move based on all the different options that this game could go from there, I have the best chance of winning. That's essentially what these artificial intelligence programs were doing to win at chess, to win at Go. Go was even harder. A piece of software did not beat a world champion until 2017. Definitely watch that video. It's another cool thing to think about. You can think of chess as having a bunch of options, right? You have, how many squares is it, 8 by 8 or something? There's a bunch of different squares that you can move things to. Go has a lot more, and so that's why that tree gets a lot wider and a lot deeper, and that's why it was harder to beat humans at. But eventually that day came, okay? And this brings up something really, really cool. The reason why this was all happening back in 97, the reason that was a long time ago, why was it relatively easy to do that but harder to do this kind of general knowledge stuff that Watson could do? Why did that have to come later? The answer is that chess is you can write down the rules of chess very easily. whereas you can't really write down all the questions that you can answer on Jeopardy very easily. Because the rules of some games like chess are super clear, a machine, this is really crazy to think about, a program can learn without any prior information. Does that make sense? It just needs to know what valid moves could be made. It needs to know what it means to win the game, and then it can just start trying all the possibilities on itself. It can play itself. That's crazy. And then it can be better than anybody ever could be, because it's playing more games than any human could play in their entire lives, learning all the secrets of chess without anybody having to write it down for them. Isn't that cool? Just write down the rules, press play, and it'll figure it out. There are some cool videos of this on the internet with like old console games, like trying to map what that means to win it into a computer, and then it was able to play all of those old games and win at those. Much better than a human could. So yeah, this is a very cool thing that happened, and hopefully you have a better idea of why it happened and how it becomes possible to do things like this inside of a computer. Are there any questions about this idea or any others? All right, so that's just a bunch of fun stories, I think. That's cool. We can get out of that and get out of that. I don't have anything new to give you, but I did give you an essay last week, and I did have a slide on that here. I just wanted to talk to you about what you're going to be doing, give you an example of what you might do for one fallacy, because I found this back in the day. So here is something to help you, how you can structure your essay. So here's an example that I found last year. Here's an example of a straw man fallacy. And this is the kind of thing that you would be finding on your essay. So here is a tweet by the vice president. She said, last year on International Women's Day, I want to honor the women for over a year who have gone to work, because this is mid-pandemic, right? Risking their health, blah, 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 all this stuff. Nice things to say, right? And then somebody replied, just the women. Guess that would be typical of you. I think all who risk their lives for others. And this would be a great example of a straw man fallacy. You would say, okay, this is a straw man fallacy because the vice president was saying nothing about other people. She was highlighting the work of women and not trying to degrade or bring down anybody else. It was just International Women's Day, and that was the point, right? To highlight things and just honor women. But what she wasn't saying was, go women and I hate men or something. Right? That's the words that this person is trying to put into her mouth. That's the idea. And that's what a straw man fallacy is. Trying to put words in somebody's mouth, trying to have them say, or trying to frame their argument as something that was not really their argument. All right? And so that's the kind of thing you'll do. You'll find a bunch of examples like this, quote them in your essay, tell me exactly what fallacy it was. They all have names. And just tell me why it was that fallacy. Okay? Does that make sense? So if you're questioning about how to start and what to find, examples like this are great. Just look at every politician's Twitter page, and you'll find plenty of examples like this. Okay? So, yeah, I think that's where I want to stop for us today. Please take the rest of the time to work on anything that's out and to ask me questions. And I can stop recording too.